In the 1990s, McDonnell Douglas developed an experimental single-stage-to-orbit prototype that few people had even heard of. The DC-X, or Delta Clipper Experimental, was designed to test rapid turnaround, vertical takeoff and landing, and reusable rocket technology. Unlike traditional rockets, it could land like an airplane and be ready for flight again in hours. This little-known vehicle laid the groundwork for what later became modern reusable rockets. The program was small, secretive, and high-risk, with only a few test flights ever completed. Engineers were testing radical concepts that could have transformed spaceflight forever. Its low-cost, quick-reuse philosophy challenged decades of conventional rocketry thinking. The DC-X showed the world that a reusable, fast-turnaround rocket was not science fiction. It was achievable. The DC-X program began in the late 1980s under a NASA and U.S. Department of Defense partnership. Its goal was to prove that a single-stage-to-orbit reusable vehicle was feasible. McDonnell Douglas engineers sought to drastically reduce launch costs. The concept challenged decades of conventional expendable rocket design. The vehicle was small, roughly 12 meters tall, and designed for suborbital tests. It used liquid oxygen and liquid hydrogen engines to power vertical takeoff and landing. The aim was rapid turnaround, with the ability to fly multiple times in a week. This required unprecedented automation and ground support systems. Unlike traditional rockets, the DC-X did not rely on large launch pads or extensive infrastructure. It could take off and land on minimal facilities. Engineers were testing vertical landing guidance, attitude control, and fuel management. Every flight was a complex balance of risk and innovation. The program was kept secret to avoid public scrutiny and political pressure. Test flights were often conducted under limited media coverage. Only a handful of engineers, pilots, and program managers fully understood the scope. This secrecy emphasized the experimental nature of the vehicle. One of the DC-X's main goals was operational simplicity. Rapid reuse meant minimal refurbishment between flights. Components had to withstand extreme heat, vibration, and acceleration repeatedly. This pushed materials science and engineering practices to new limits. Even at this early stage, the DC-X attracted attention from aerospace visionaries. Its potential influenced later concepts for fully reusable launch vehicles. Engineers and planners saw the promise of dramatically lower costs. The program set the foundation for future rocket experiments. The DC-X made its maiden flight in August 1993 at White Sands Missile Range. It successfully lifted off vertically, hovered, and then executed a controlled landing. This validated the vehicle's guidance and control systems. Engineers were immediately encouraged by the precision and reliability demonstrated on such an early flight. Subsequent flights pushed the vehicle further, testing longer durations and higher altitudes. The DC-X repeatedly demonstrated vertical takeoff and vertical landing capability. Fuel management and attitude control were refined with each iteration. Rapid turnaround between flights became the central focus of the program. Despite early success, the program faced technical challenges. Minor engine malfunctions and hydraulic failures occurred during several test flights. Engineers responded quickly, adjusting systems for safety and efficiency. Each problem provided crucial data for future reusable vehicle development. The DC-X proved the feasibility of rapid reuse in rocketry. It completed multiple flights within days, far faster than traditional expendable rockets. This concept challenged decades of standard aerospace operations. It demonstrated that rockets could be treated more like airplanes in terms of turnaround. Flight tests included hover, transition, and simulated landing from higher altitudes. The vehicle's computer systems adjusted throttle and attitude automatically. Each test incrementally increased confidence in the concept. The program validated that vertical landing could be precise and repeatable. By 1995, the DC-X had flown multiple times successfully. The program had demonstrated that single-stage, reusable vehicles were possible on a small scale. Its performance impressed engineers and planners worldwide. The vehicle had proven that the future of cost-effective spaceflight could begin here. The DC-X reached heights and durations that no previous reusable rocket prototype had achieved. It hovered for over 2 minutes while maintaining precise vertical stability. Each flight pushed the limits of automation and guidance systems. Engineers documented every metric, knowing each success could revolutionize spaceflight. The vehicle consistently demonstrated repeatable landings, proving the concept was viable. Rapid turnaround became a defining achievement. The DC-X was refurbished and ready to fly again within 26 hours on one occasion. Traditional rockets required months of preparation between launches. This efficiency hinted at a future where launch costs could drop dramatically. It fundamentally challenged assumptions about operational rocketry. The program also tested thermal protection and structural limits. Heat shields endured multiple flights without major damage. Propellant tanks, fuselage, and control surfaces were stressed repeatedly. Each test informed material selection for future reusable spacecraft. The DC-X became a laboratory for real-world engineering extremes. Flight control systems were fully automated for most operations. Pilots only intervened in emergencies. This was revolutionary for the time, reducing human error and increasing safety. Autonomy allowed flights to reach new precision levels. These tests laid the groundwork for fully automated reusable launch systems. Engine performance also exceeded expectations. The throttleable hydrogen-oxygen engines allowed controlled ascent, hover, and descent. Fuel efficiency was carefully monitored to optimize rapid reuse. The DC-X demonstrated that precise, rapid control propulsion was achievable. This innovation directly influenced future designs like SpaceX's Falcon 9 and Blue Origin vehicles. Despite the success, risks were ever present. Minor explosions and hard landings occurred during testing. Engineers learned quickly, redesigning components to improve reliability. Every accident contributed to a deeper understanding of reusable rocketry. The program proved that failure was part of the innovation process. By the end of its test program, the DC-X had reshaped aerospace thinking. It showed that rockets could operate more like airplanes with quick turnarounds and repeated use. The lessons influenced NASA, commercial companies, and military planners. Few vehicles in history had so clearly pointed the way toward the future of spaceflight. Despite its successes, the DC-X program faced significant political and budgetary challenges. Funding was limited, and competing projects like the Space Shuttle received priority. Congress was cautious about allocating more money to a small experimental vehicle. These constraints ultimately slowed the program's development. Technical setbacks also contributed to program uncertainty. A landing accident in 1996 caused damage to the vehicle's lower fuselage. Repairs were costly and time-consuming. Although engineers quickly addressed the issues, confidence in long-term funding wavered. The program's secrecy limited public and political support. Few outside the aerospace community understood its revolutionary potential. Without widespread recognition, it was easier for decision-makers to cut funding. This left the project vulnerable despite clear technical achievements. NASA and the Department of Defense explored follow-on concepts. Concepts like the X-33 and VentureStar were partially inspired by DC-X lessons. However, these programs faced their own technical and financial hurdles. The DC-X's small size and simplicity made it more successful as a testbed than as a full operational prototype. Even after the program ended, the DC-X influenced future aerospace design. Engineers studying its flights applied lessons to automated landing, fuel management, and reusable structures. The idea of rapid turnaround rockets gained credibility. Its design philosophy echoes in modern reusable rockets today. Military planners also observed its potential for low-cost launch capability. The concept of quick-response payload delivery attracted attention. Although never deployed operationally, the DC-X shaped thinking on responsive space launch. Its ideas directly informed future strategic planning. Ultimately, the DC-X program ended not because it failed technically, but because the timing and politics were not aligned. It had proven its core concepts beyond doubt. The lessons survived long after the vehicle itself was retired. The DC-X became a symbol of what could have been possible for spaceflight. The McDonnell Douglas DC-X proved that single stage-to-orbit and rapid reuse rockets were technically feasible. Its vertical takeoff and landing design challenged decades of conventional thinking. Every successful flight demonstrated automation, precision, and operational efficiency. Although small and experimental, it had a disproportionate influence on spaceflight design philosophy. The DC-X directly influenced NASA's X-33 and VentureStar programs. Lessons learned about fuel management, flight control, and thermal protection informed these follow-on projects. Engineers used its data to refine reusable spacecraft concepts. The program validated that reusable rockets could drastically reduce costs and turnaround times. Its legacy extends to modern commercial spaceflight. Companies like SpaceX and Blue Origin implement principles first tested on the DC-X. Vertical landing, rapid refurbishment, and autonomous flight are now standard for reusable rockets. The vehicle's design philosophy lives on in today's aerospace industry. Even though it never reached orbit, the DC-X demonstrated the future of space travel. The program's small-scale, low-cost approach proved that experimentation can outpace bureaucracy. Rapid iteration and testing became a model for aerospace development. Its pioneering role reshaped expectations for what rockets could achieve. The DC-X also inspired a new generation of engineers. Seeing a functional, reusable vehicle motivated future designers and researchers. The program showed that spaceflight innovation does not always require massive budgets. Ingenuity, vision, and careful testing can achieve breakthroughs. While the vehicle itself is now retired, its flights remain legendary. Only a handful of prototypes ever achieved what the DC-X did. Its hover, landing, and turnaround records still stand as milestones. The program is remembered as a turning point in reusable rocketry research. Ultimately, the DC-X proved that the future of spaceflight could be radically different. It was a small rocket with a huge impact on aerospace thinking. The lessons it generated continue to shape technology, strategy, and exploration. Its story remains one of the most influential secrets in spaceflight history.